Hi, I'm Ben-Yaakov. This presentation is entitled An Intuitive Insight into Electric Vehicle Wireless Power Transfer Charger at Resonance. I'm talking about a charger for a car battery. It's going to be high power. We have an excitation here or an input. Usually it's going to be a full bridge, could be half a bridge for a lower power, which generate a square wave, which fed into the transmitting antenna. This is the antenna here, and this is the inductance of the antenna. And then we use a capacitor for resonance so that there be a better transfer of energy between input and output. So there be cancellation of the impedances. And then we have the receiving part. This is the receiver antenna and the capacitance. Then we have a rectifier. Usually it be some capacitance to capture some of the ripple current. And then we have the battery. Now these two antennas are actually mutual inductances, okay? And the relationship is K, which is the coupling coefficient, square root of L1 and L2. I'm assuming in this presentation that the inductances are the same just for simplicity and not to complicate the equation. And in this case, the mutual inductance is equal to the coupling coefficient times the inductance. Now the resonance frequency of the circuit, of course, with the C and L, is 1 over square root of LC. This is the circular frequency. Now the coupling coefficient is a function of the coupling, between the antennas, and it is dependent on the distance between them. Obviously, we like to put them one above the other and as close as possible, but in real applications, there is going to be some distance, and which could be changing from situation to situation. And then as the distance is increasing, and this is the distance between these antennas, the cross-section here, then the coupling coefficient is going down. These are like real numbers. Usually it'll be below 0.5 for an antenna like this, and down to 0.1 or even lower than that. So we're talking about very loose coupling between the antenna, and this is something to worry about. I'll talk about it, of course, in this presentation. This is a major issue in this power transfer. Now we are feeding a square wave into the antenna, the transmitting antenna, but the current is usually going to be very close to a sinusoidal waveform. Now the reason is that the quality factor of this circuit is going to be high because the losses, like the parasitic resistance, is chosen to be very small to lower the losses. So therefore, we basically see the first harmonic, and this affects the power transfer. So we're going to see here a flux here, which is sinusoidal. And then also we have here a resonance here, but the voltage here at the input to the rectifier is going to be square wave because the battery is clamping the voltage here to the value plus the voltage drop on the diode. So we're going to have a square wave here. Now, it is customary to work with the so-called first harmonic approximation to simplify matter because this circuit is highly nonlinear. Okay, we have the rectifier, we have square wave, and then, of course, you cannot use the phasor analysis, okay? So the thing to do is actually to rely on the fact that, in fact, power is transferred through the first harmonic, as I have said. Then, therefore, we extract the first harmonic here and the first harmonic here, and then by this we can actually make the circuit linear. Okay, so let's see how we do this. We have here a square wave. A square wave, the first harmonic of the square wave is 4 over pi. This is the peak value. 1 over square root of 2 is the RMS. So the RMS, this is now RMS, small letters here, is the input voltage to square root of 2 over pi, which is about 0.9. Okay, so the first harmonic, sinusoidal harmonic here, is 0.9 of the DC here. Now, the same thing we can do at the output. We have here a square wave of the battery voltage, and therefore the RMS, V small b here, phasor variable, is 2 square root 2 over pi over this, which is again times 0.9 of the battery voltage. Okay, by this we have actually got rid of the square wave here. Now we can also replace the load by an equivalent resistance of the same power, of course. And now the power, if this will be a resistance, then the power is going to be V squared over RB, from which we can get a value of RB if we know what is V squared and what is the power level that we are now charging the battery. Okay, so this will be the expression for this equivalent resistance. And from here we can get again what is the battery voltage, and then the relationship between the DC to the battery and this phasor value here, IB, the first harmonic approximation. So by this, we actually converted this nonlinear circuit with a square wave into a linear circuit in which the feeding is sinusoidal and the load, okay, is also linear. So now the system with the first harmonic approximation looks like this. We have these are the parasitic resistances. Well, at high frequency you have to consider the RAC, the skin effect, of course. And then we have the resonant capacitor, and these are the inductances. And here already I've put here the first harmonic approximation representation here. Now we can analyze this circuit two ways. One is by considering this coupling as a transformer, okay? And this will be like a equivalent circuit of a transformer. And this is the leakage inductances. This is the common inductance between input and output. Again, the transfer is 1 because we have the same inductance here and here. So this is a simplified circuit. These are the resonant capacitor, and these are the parasitic resistances. And then we have here another way of representing this circuit, and this is by the physics textbook of mutual inductance, okay? Here, we're actually breaking the connection here, but replacing it with dependent voltage sources. Now, this dependent voltage source depends on the current of the secondary, and this one on the current on the primary. Now, positive current are actually going in, and I've marked here as going out because this is more realistic from the physical point of view. So this is why we have here a minus, okay? So these two circuits represent this coupling, but in another way. This is very convenient, and I'm going to explore this approach and actually rely on it further on. But let me go back for a while to this way of representing the system and to point out something very, very important. When we look at this circuit, we think that we have one resonant here, okay? This is between this capacitor and this inductor, and this capacitor and this inductor, and if these inductances are the same, capacitor are the same, then we have one resonant. But if you look at this representation, taking into account the coupling coefficient and the breakdown into this leakage and common inductance, we realize that things are not that simple here. For example, if the equivalent resistance is very high, this is like open, you have one resonant circuit. So first of all, you see that you can develop here very high voltages. Although the impedance of the inductance is sort of cancelled out by the impedance of the capacitor at resonance, you see that the voltage across this inductance could be very high because of the resonant, and depending on the quality factor, the current can be very high. So you can develop here very high voltage, actually higher than the input, okay? And then if the load resistance is very small, let's say it's a short here, you see that you can actually have two resonances here. You have between this and the rest of the circuit, and then between this and another part of the circuit. So you might have two resonances, and in fact you do have it, and I'll show it later on. Now that we have this equivalent circuit, we can actually simplify methods quite a bit by using the Thevenin theorem, which means that we can represent the whole thing as one source and one internal resistance, okay? Now to do this, I'm first of all finding what is the voltage, the open circuit voltage here. And if this open circuit here, there's no current, and therefore there's no voltage here imposed by this dependent voltage source. And we are at resonance, so the current is V in over R1. Here it is. And then it is reflected here times j omega m. And this is what we see here at the output times this value here. KL is the mutual inductance. Now defining the quality factor is omega L over R, the resonant frequency. We found that this is the open circuit voltage here. Now you can see again that if Q, the quality factor, is high, and in fact it's going to be high in this circuit because the resistance is going to be low, then you can have here a voltage which is higher than the input, and this is consistent with the other way of looking at the circuit that I've just shown here. Okay, we can also represent the quality factor as a square root of LC over R, when this is the characteristic impedance, and of course these are the same thing here. So this is the open circuit of the Thevenin equivalent circuit. Now we can find the internal resistance, and this is by injecting here a current, having a short here. If I'm injecting a current, then this value of this voltage is j omega times this current, of course, divided by R is the current, which is then being reflected here back, and therefore we can find the voltage here, and if we know the voltage divided by the current, we have the impedance, we have the resistance, and again I'm neglecting here the parasitic impedance as compared to this value here, and I come up with this relationship for the equivalent resistance, internal resistance of this circuit. Okay, so it's K squared, the quality factor square, times R1, and therefore this is now the equivalent circuit. And this we have found by converting the battery voltage to a first harmonic approximation load. And this is now the Thevenin equivalent, okay? Thevenin equivalent meaning that this is the equivalent input source, and this is internal resistance. Now be aware that Thevenin theorem is not energy conservative. That is, this RT is sort of imaginary. There are no losses here, okay? There are no losses here. And therefore, when you come to calculate the losses, you should only take this into account. Okay, this is sort of a lossless resistor, you might say. So this simple system, however, allows me to do many, many things. For example, I can then go back and see what is the current here, which is, of course, related to the charging current of the battery. And this is this expression. And then from here, and knowing the current and multiplying it by RB, this is the equivalent resistance representing the battery, I can find the ratio between the output voltage, this is the first harmonic RMS here, and the input RMS here. And this is the expression. This is a very, very important equation. We see here that we have here the coupling coefficient, the quality factor, the load, and also we have it here. Again, I've neglected here the parasitic resistance of the secondary. Okay, now this ratio, which is the first harmonic approximation, is equal to actually to the large signal or the battery voltage over the input voltage, because the coefficients are the same for the two, and therefore this is a very, very important equation. We'll see it later on. Now, what about the losses or efficiency? Well, the losses are due to current passing through R1 and R2. Now, as we have an equivalent circuit, we can calculate these, but I'm not going to do it, although I've written some expression here, because the final expression, when actually opened and with all terms in, it's going to be kind of complex. And I think that the best thing to do is, once you have all these values, just to run a simulation, and then you can very easily find the losses and the efficiency, etc. So I'm not going to elaborate on this anymore. So after we got all these expressions, let's see how we can use them in a very simple design, a basic one-point design. By one point, I mean that we're going to work at resonant, not off-resonant, although I'll talk a little bit about off-resonant later on, but not here. But this presentation is concentrating on operating the switching frequency at resonant. So we are talking about working at resonant for a given requirement like battery voltage, input voltage, etc., charging power. And from this expression, we can find what should be the inductance of the antenna and the capacitance of the antenna to get the optimum operation. And by optimum operation, I mean having the lowest losses. I'll talk about it a little bit later on. So I'm assuming that I'm given this information. And this is the coupling coefficient, equivalent resistance that represent the load, parasitic resistance of the primary, secondary, at this stage I'm neglecting, and the desired ratio between the battery and the input. That is, if I have a 400 volt battery, I may wish to work at 400 volt or 800 volt or maybe 300 volt. So this is something I decide when I'm specifying the system. Now, this equation now allows me to get what is Q. Now, Q is equal to omega L over R1, okay? So I can now, once I know this quality factor, I can decide to choose a given frequency and then calculate the inductance from which I calculate the capacitance. Or I can, if I have a given antenna, if I have the antenna, I can calculate what is the resonant frequency from here, and then, of course, the capacitance. Now, to get Q, you have to solve this equation, okay? This is a second order equation, which I'm not opening here and representing it as such. There are some tools that you can very quickly find what is the solution for Q1 in this equation, assuming that you know everything else. That is, you know what is the battery, the input, battery voltage, input voltage, equivalent resistance depend on the battery voltage and the power, and then the parasitic impedance, and of course, the coupling coefficient. And again, this design is for a given coupling coefficient. And here is an example. Now, using the approach I've just shown with the equation, I can get all the values of the frequency, inductance. This is given, of course, the parasitic resistances, and this has been calculated from the equation. Quality factor is 126. And the coupling coefficient is given as 0.2. And I'm assuming that I'm going to charge the battery of 400 volt by 10 kilowatt, which is 25 amp. Now, from this voltage and the 25 amp, or the power, I can find that the equivalent resistance for this particular operating point is 13 ohm. And let's assume in this example that I want a ratio of 1 between the battery voltage and the input voltage. Okay, 400 volt output and a power supply of 400 volt at the input. So I'm going to show a simulation of this case, and also I'm going to show a simulation of another case in which I'm assuming that RB now is 50. Okay, so it's off the relationship that I've calculated, and we're going to see what will happen in simulation. And from the calculation, that is, if I'll, for what I found, the quality factor that I found, I'll put here 50 ohm rather than the 30 ohm, which are the nominal value according to all these parameters, then I should get this ratio here. So to run it, I've just set up this very simple schematic. This is a coupled detector. Coupling coefficient is the 0.1, and these are the parasitic resistances, inductances, etc. This is now an AC. This is the output. And this is now the load that would be either 13 or 50. Okay. So first of all, let's run the 50 ohm. This is this equivalent resistance. And here it is. So you see that at resonance, we find that the gain is indeed 3.4. We see the resonant here, and the resonant is 84 kilohertz. Now, if we move with the frequency, then you see that the gain is changing, and also the phase is changing, which would mean that the current of the antenna will be shifted in phase with respect to the excitation, meaning that you have reactive power. You like to have a little bit of a shift, actually a lagging of a current, to get soft switching, but of course not a large shift. Okay? So this is not the actually operating point. Now the operating point of this example is this simulation in which the RB is 30 ohm. And according to our calculation, it should be a ratio of 1. And here you see the splitting here. The resistance is small, and therefore we see now actually two resonances here, okay? And here and here. And due to this extra resonance, there is a shift in the gain. So the equation now is not taking this into account. It's a little bit off. And you see that it's rather than 1, it should have been, it's about higher than that, 1.1 or something like 1.5, which is off. Well, this really complicates things, but this is real life. This is the situation that we have to live with. And then, of course, maybe do some iteration and correct for it and get the right number. But again, this is for one point. This is for one battery voltage, one current, one ratio between input and output, and in particular, one coupling coefficient. If any of this will change, there is a problem. Okay? Now let's have a look at this extra resonant point from another point of view, which maybe clarify it a little bit better for those who are a little bit baffled with this. I've shown this circuit and I explained that if the impedance here is low, let's say short, you can have a resonance between this capacitor and some of the inductances here, and at another frequency, another resonance with this capacitor and the rest of the circuit. Now we have represented this circuit by a Thevenin equivalent circuit, okay? And in this case, this was a resistance. Now, this was for operating at a resonance, exactly as resonance. Then this is going to be a resistive. But if you move from the resonance to another frequency, this impedance becomes reactive, okay? And then it might have some resonant points. And therefore, the Thevenin is okay, but then for off frequency, you cannot assume that this is a real resistance. So this perhaps sort of clarify a little bit more this whole issue. Now, up to now, I've just shown simulation of the first harmonic circuit, the equivalent circuit. Now, what about the real circuit? What about the nonlinearity of the diode and the battery, which is a constant voltage, and the fact that we have a square wave and not a sinusoidal waveform as we assume in the first harmonic oscillation? So I'm now running this circuit, full-fledged, time domain, transient analysis with the parameters of the previous example. Okay, the same circuit, only now it is the real circuit rather than the equivalent. And here is what I'm getting. First of all, you see that we got 25 amp to the battery, which is the target of the target, 10 kilowatt, 400 volts. And then we see the input as a square wave, plus minus 400 volt. In the first harmonic approximation, we assume, of course, that this is like a sinusoidal input, the first harmonic only. What is very important is the current of the antenna at the primary is in phase with this square wave, meaning that we really don't have any reactive power, except for the higher harmonics of the square wave, which are really not involved in the losses because the current is sinusoidal, okay? The parasitic resistances see a sinusoidal waveform. So this is an excellent situation, and this actually verifies the equation of the transfer ratio between the input and output voltage. And now comes the question. If this equation sort of locks the relationship between all these parameters, then what will happen if I'll design it and then say the coupling coefficient will change because the distance between the antenna is not fixed, it could change, okay? So in this case, obviously I'll be off, and this will not be an optimum point in that the current will not be in phase with the voltage, and also the gain will not be what we expect. Like if you change the coupling coefficient, then of course the gain will change. So how can we correct for it? Well, there have been numerous papers that have been published on this subject, and they're coming up every year, every month, more and more, because this is a really sore point. There are many approaches. One of the popular approaches is using matching circuit. The idea is the following. Suppose the coupling coefficient has changed, okay? And therefore there is a mismatch between these two sides of the equation. You can correct for it by changing RB. Now, obviously, I don't want to change the power delivered to the battery, but I can use a matching network such that when looking into this matching network, I'll see a different RB such that it will correct this, so this equation will be valid again. Now, this matching circuit could be passive based on, say, capacitors, but this would be for one point, or it could be variable, and this would be dynamic, active circuit like a converter, okay? A switch mode converter actually is a matching circuit. If you have a load here and you look at the input, you see a different resistance. In fact, like in a buck converter, so the input impedance will be the output impedance divided by d squared, the duty cycle square. So by having a converter which is placed after the rectifier, between the rectifier and the battery, in fact, then we can actually do a impedance matching or a load matching, and then to go back to the operating point that we want to work at. So what are the conclusions of this presentation? Now, for a given set of parameters like the battery voltage, input voltage, etc., there is actually only one set of L and one value of L and C that will ensure optimum operation. Okay, there's only one. Now, any deviation of, say, the coupling coefficient or the battery voltage, or if you like to charge the battery with another power, will actually move the system in a non-operating point. This will cause a reactive current and increase losses. Now, load matching can alleviate some of this problem. This is one way. There are other ways to do it. But the point is that once you move from the nominal point, you have to do something in order to go back to the desired operating point. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.